All right. So, thanks, Professor Pandy, for that awesome talk. At this point, we're going to go into the distributed simulation demo from the Voices project. And to carry most of the weight here, we're going to invite Danielle Chou, who is the Enabling Technologies Program Manager at the Federal Highway Administration. She will give a talk. Then we will transition back local and show a video where I'll do the voiceover thing again for you. And then we'll bring Danielle back for the Q&A session. So take it away, Danielle.
If I unmuted myself. Thanks, Derek. My name is Danielle Chou, and I'm a program manager for Enabling Technologies at the Federal Highway Administration's Office of Safety and Operations Research and Development. And I am very pleased to introduce today the multi-agent distributed testing demo that Derek mentioned earlier. Right, so hopefully my slide has progressed. There we go. So specifically, we're going to see a replay of an event from our Pilot 2 test campaign this spring, in which FHWA, Mcity, and 6 other organizations were able to connect over a secure network and co-simulate together using a mix of simulated and physical test assets across the country. So the full research team collaboratively identified research objectives around co-simulation, as well as the advancement of cooperative driving automation, or CDA, by accelerating development of standards and norms for heterogeneous multi-agent environments. So what does it take to do a distributed test, a multi-site distributed test? Really, you need 4 key components. The first is the secure network to connect all the partners. And for this, we use Voices, which is a DOT-funded networking portal that has been tech transferred out of government and is now operated by a MITRE corporation. We also need a common language, so different organizations have a consistent way to exchange data and don't need to keep reinventing that protocol every time they have a unique partner. For this, we're using the Department of Defense's Test and Training Enabling Architecture, or TINA. Next, we need a common scenario which helps all the test partners join in a shared reality. And the scenario is defined by digital maps, object initial states, and other input files. And then lastly, we need test elements, which can be digital or simulated and under human or automated control. But the gist of it is they all need a basic digital representation that we can observe in the co-simulation environment. But otherwise, they can remain black boxes to each other, which allows them to protect intellectual property as necessary. So for Pilot 2, it was very exciting because our joint test was conducted by 8 different organizations all across the US, as you see on this map. So we had 2 groups of academics, of course, Mcity, but also UCLA. And then from the private sector, we had Econolite, Volkswagen, and the Traffic Technology Services, TTS, which on this map is shown in Oregon, but technically their available staff member was sitting in Edinburgh, UK. So truly, we have actually now demonstrated and experienced a global test. And lastly, on the government side, we had FHWA, as well as Argonne National Lab and Oak Ridge National Lab. So what I really want to highlight with this chart is that through distributed testing, the research community is able to collectively now pool its resources to study complex problems that would be very expensive and hard to tackle otherwise. We had unique contributions from every single research partner in our group, and Mcity was a huge contributor by bringing its digital twin, its simulated naturalistic driving model, TerraSim, its live vehicle on track, as well as its virtual VRU. So really, our distributed testing project benefited from Mcity 2.0 because we had very similar objectives in many ways, right? We're all striving to foster collaboration, which is why the open source digital twin was crucial in enabling all of our research partners to work from that same map and to open the facility up to a multitude of simultaneous users. So track time was no longer this hard constraint. We were able to also reduce costs because by testing in simulation, that helps make track time more efficient, and it also minimizes the cost of travel. Lastly, we aim to improve the safety and efficiency of the system, as well as of the development process. So for instance, using Mcity collected pedestrian data, we played that back through the co-simulation to help assess other parts of the intersection ecosystem, whether that it be V2X communications or the human or automated driver response. So I mentioned that Pilot 2 was a test campaign because it had 3 events, each of them answering unique research questions. The first event, dubbed Event 0, was able to affirmatively answer that, yes, multiple sites could simultaneously co-simulate and interact with microtraffic and each other across a cloud-based network. So all 8 sites gathered on the Mcity digital twin, and we had a little bit of a virtual race in which every site was manually controlling a car around the track. And yes, there were a few reckless drivers who crashed into others, but that was kind of the point, right? Confirming that we could interact in that safe environment. This was followed by Event 1, in which a subset of our partners gathered to begin answering the research question, how compatible are 2 different VRU-related standards? In this case, both SAE and the European Telecom Standards Institute, or ETSI, have taken different approaches to their cooperative perception standards. So we wanted to collect data that would potentially help us understand what are the system level performance differences across the 2 different types of standards. So to do this, Mcity collected tracks of pedestrians walking around on their facility, which we then replayed over the secure network to both TTS and Volkswagen. And you can imagine how a future test might observe whether or not a vehicle model could respond the same or equivalently or very differently to the SAE versus the European standards. Because that kind of information would be very useful to the OEMs as well as the standards development organizations. And with that, I'm going to turn it over to Derek to talk about Event 2, which is our most complex distributed testing.
Thank you, Danielle. So before I get started here, I do want to thank you for bringing up that crash that you mentioned in the Event 0. Prior to the event, the night before, we all got together and we decided that there would be no reckless driving, that the idea was to get through this without any issues whatsoever. Fast forward to the event, I'm out there engaging in a head-on collision with one of the other participants, and it wasn't just a simple head-on collision. The cars went toppling over, and I just sat there hoping nobody noticed that, but apparently somebody did. So thanks for bringing that up, Danielle. So what we have over here on the right is our the beginning of our video, and as Danielle has kind of set the scene here, we have 5 different participants in the top left that are going to be our autonomous vehicle string. And what is so special about this particular demonstration is that each one of those autonomous vehicles is running a completely different autonomous stack. They need not share any of their secret sauce or their proprietary information with each other. They're just sharing position and some kinematic information that is being sent back and resimulated at each of the distributed locations. So when the video does start, those 5 will set off on their way. There are a couple of other actors. I'll come back and give you the individual actors of that particular string. But down in the south there, we have TTS. They are driving manually from a computer keyboard like you would for a video game. And in the bottom right, we have Volkswagen doing the same thing. We wanted to include them in this final test. They were heavy contributors to previous events. So they are doing the keyboard driving that I was doing when I caused the wreck. Maybe I didn't cause it. I think it was the other guy. I don't know.
I think it was the other guy.
At the intersection there where we see a yellow and a red, Econolite was also one of the distributed simulators, and they were sending out signal phase and mapping messages to describe the intersection and the current state of the lights. And that was also shared with everybody. So all of these autonomous vehicles knew what those lights were, and we rendered that on on our digital twin here. I will say that this is a very early version of our digital twin. We recorded this back in May, so you can see how far we've come based on what Darian showed us earlier. So this is what a few months of hard work and having excellent partners like Quantum Signal can do. So I think I've got that. I just need to introduce the 5 vehicles before we start. UCLA, it is up front, and they were pure simulation. Argonne National Labs was next, and they were a mixed reality simulation. You can see in the very top right, a little silver vehicle that's a Chevrolet Bolt hooked up to a dynamometer. I encourage you to kind of watch the Argonne vehicle and wait for it to move. You'll see the wheels in the front moving. So the autonomous platform is on that vehicle, driving that vehicle, and sending the wheel speed back to the simulation, and that is sent back to everybody, and so that each distributed simulation can render. Third on the list is Oak Ridge, and they are pure sim as well, running their own different, again, a totally different autonomous stack. Mcity is fourth, and we were a mixed reality. We had our real vehicle here being driven by an autonomous platform, and we were gathering that GPS location, mapping it to this simulation, and sharing that with everybody as well. And bringing up the rear was the Federal Highway, and they were full, the Federal Highway Administration vehicle, and they were full sim as well. More on the Mcity, I skipped right over it here. The dash cam and the infrastructure chase cam are at the bottom of that inset in the top right there. So again, I encourage you, as this video goes through, you'll see the real vehicle, kind of as proof that we actually did do this on our real facility. You can see the infrastructure cameras and the dash cam as well. So I think with that, we can probably run this. Go ahead, Vince, and run this video. Thank you. So we're off to the races. You see UCLA out to an early start. Argonne and Oak Ridge are going to follow closely behind. And as proof that these are different autonomous platforms, those 3 are a little bit more aggressive with their following distances. The final 2, Mcity and Federal Highway Administration, are a little bit more conservative. They have longer following distances, so that string will stretch out as they spread across the facility. At this point, you can kind of see Volkswagen has started its maneuver, and from the bottom we have TTS coming north. You also see a TerraSim vehicle. Completely forgot to mention those earlier. We are going to be spawning some TerraSim vehicles in here to kind of give some background flavor. That TerraSim vehicle is currently at the intersection and stopped at a red light. The string here is moving along. We are now doing a chase cam view, and you can see in the top right, you see that wheel moving. And you also see the dash cam moving and updating for the 4th place vehicle, the one right in front of the vehicle being followed right now. At this point, you'll see TTS come up from the south, and they will come to a stop and graciously let that string pass through the intersection. The TerraSim vehicle has just gotten its green light and is moving through the intersection where the light is, and the string has gotten the red light. So they're all going to kind of stop and follow their own following distance rules, and then wait for that intersection to turn green. Here we have the TTS vehicle. The TerraSim vehicle just despawned. The TTS vehicle is waiting for the final vehicle in the string to clear this intersection that we're looking at right here. Okay, we've gotten the green light, and that string is now moving on to the roundabout, where it's going to proceed back north. And again, I'll call out the moving vehicle, the moving wheel up here on Argonne's chassis dynamometer. And there you see the second TerraSim vehicle just despawned in the bottom right of the view there. And the string is quite spread out now because of the differences in the autonomous platforms. So this was actually pretty exciting demo to put together, because personally I've never done anything like this where we have 5 different autonomous stacks all performing at the exact same time. It allows for a lot of interoperability testing, how each member of the distributed simulation behaves and can affect others. And the end of this test will be when the string reaches the north traffic circle there, that they're just about reaching there too. I think we're going to get one more chase cam view of that final vehicle. So as we pass through the final intersection here, you can see the Argonne vehicle has come to a stop, and that front wheel is also coming to a stop. We're getting the dash cam view of the Mcity vehicle there as it's passing through that north traffic circle. And the Federal Highway Administration is now finishing its run as well. And that is pretty much it. So that's our demo of the multi-agent, the distributed testing. And with that, I'm going to bring back Danielle Chou, and we can do a brief Q&A session if we're on time. We good with that? I'm getting the thumbs up.
So you said you were sharing the information between the vehicles. So were the other stack using that information, or they were just like doing their own autonomous stack without leveraging that?
Well, they were definitely using the information.
And what was the protocols you were using to share? Because everyone is kind of running their own stack. So is there a protocol?
Danielle, would you like to take that one?
Me?
Yeah.
Sure, I can answer that question. So I had mentioned that there's a common language that we use across all the test partners called TINA. And so we use that to basically send around two types of information. Ground truth data, so ground truth state data, and then message data. And that's pretty much all that's sent around to keep the network as lightweight as possible. And all the rendering happens on the edge at each of the sites.
Okay. I can add a little bit to that. I think the TINA communication backbone had a way of creating TINA adapters, and there was a J2735 adapter. So when a vehicle's position came in, it was converted to a J2735 message that was perceived by the vehicles at the various distributed testing sites, and so they were made aware of the other vehicles' positions that way. Okay. So,
Question here. Sorry, NSF can go ahead.
This is not as an NSF question. I know it's the point of the exercise is just to show that all these different systems can be on the track at the same time. But I was just wondering why the separation, why they maintain it even when they're stopped? Why isn't it like velocity dependent? I mean, because people at a traffic light fill in, they tighten up and then they separate out when they start again.
sure. I think I'll start this one, Danielle, if you want to jump in
Yep.
and
Yep.
correct me, perhaps. But I think that would be a question for the individual actors. In our case, Mcity was running on AutoWare, and I actually don't know why we had such a long following distance. The Federal Highway Administration was the other one that had a long following distance. And I'm fairly certain that was a configuration set on purpose. But Danielle, do you remember the purpose of that, or?
So we had discussed this amongst the partners, and our speculation was that both Mcity and FHWA have hardware-based platforms. And so as a result, they tend to drive much more conservatively than some of the simulation-only models. So it really came down to whatever the following distance logic was on each of the individual platforms. So that's where you see that diversity of response. And I will also mention, right, as a result of this test, we saw how the systems interacted with each other. So I think almost every vehicle model ended up being retuned slightly to achieve slightly either more aggressive or more conservative performance, which we only found out because we're testing together.
So my question is somewhat similar, but we kind of try to interested in learn what are the biggest kind of lesson you learned from this distributed testing, and also from the research point of view, what do you see as a kind of for future problem that we need to look at?
I'm going to turn to Danielle for that one as well. But I can follow up as well. So.
Okay, sure. So biggest challenge is actually logistical. It was trying to get all of our schedules to align and all of the research test assets to be available at the same time. So we do foresee, a little bit of additional development to make it easier to test offline and do integration on your own before you test with everybody else. So that's one. To the second question regarding how do we see this being used? I know we talk a lot about interoperability testing, but I think a lot of it is also systems integration testing. So at this point, with so many diverse actors in the ecosystem, this is system of systems integration. So when you have everybody behaving with a low level of coordination, but mostly acting of their own of their own volition, right? Then you have to be able to do a little bit of systems integration testing to make sure when you get into the real world, there's fewer conflicts, if at all possible. Derek?
Yeah, so one of the guises under which we built this demo was the idea of collecting econometrics. Now, it turned out that for various reasons, we had to run the real vehicle at around 10 miles per hour, and it turns out when gathering those econometrics, 10 miles an hour as a top speed is really going to make it difficult to pull useful data out of the noise. But it was a great proof of concept of multi-agent testing and distributed testing, and it was a great showcase for Mcity 2.0 that we can patch it into just about any system out there, and we can work well with others with the new technology here at Mcity 2.0.
A quick question is latency more critical in this scenario if you scale up to more vehicles, you think?
Yeah, I think I'll pass that one to Danielle as well.
So okay, so for starters, I will say that this is the early phase of testing. We're still trying to understand what these systems look like, what these test systems look like. What we observed was on average about 50 milliseconds of data, 50 milliseconds of latency. And that was true pretty much regardless of how many test parties we had. But in that first event 0, we did observe some congestion based on the way we had set up the data collection. So it is a little bit dependent on how you set up the test systems as well as what data is exchanged over the network. But at this time, we don't see any showstoppers for being able to scale up.
Yeah, I have one more question. So for this setup, I was wondering if it's amenable to testing like collaborative perception, sharing sensing data in some form, whether it's post-process sensing data or maybe some intermediate fusion data to help coordinate situations where there are blind spots. Yeah, it seems like it could be a potentially interesting use case.
Go ahead, Danielle.
Yeah, you want me to? Okay. Yes, absolutely. And that's why actually event 1, we called our interoperable VRU sensing message test, because we do believe that it is, there's an opportunity to test cooperative perception through this kind of setup. That said, we would not be passing around we would not be passing around sensor data, right? We'd be passing around states. And then there could be, say, an infrastructure or a vehicle sensed track list, right? And that process track list is what gets passed around. That data can then be fused locally, or it can be used as is. So that's where I see there are nuances to the way we would test cooperative perception, but it would not be necessarily flooding the network with all of the raw sensor data. It's got to be processed first before it's shared with all the other partners.
Great question. Okay, I think that about wraps it up. I want to give another round of applause to Danielle. Thank you for joining us.
Thank you all. Fantastic job to Mcity. We were very excited that you all were able to participate.